Okay, probably the quickest of the Physics 1 topics and the last of the four. Particles. So, first section of this is density. When we talk about the density of a material, it's how much mass there is for its size. So a really dense material would be something like lead or concrete, where if you have a piece of it, it's really heavy. There's a lot of mass there in that small size. Whereas a low density would be something like polystyrene or bread. So they're really light for their size. So obviously the equation for density, which you'll get given, density is mass divided by volume. Make sure you can rearrange it. Important that you remember, always convert the mass to kilograms, the volume to meters cubed. So in the example here, what is the density of a bar of gold if its volume is 350 centimeters cubed? First of all, that's converted into meters cubed, and the mass is already in kilograms, so that's fine. There's my calculation, mass divided by volume, and there's my answer. In a meter cubed, there's 19,314 kilograms. And then in this table here, it just gives you some typical densities. So water has a density of 1,000 kilograms for a meter cubed, a ton. Glass, you can see, is more dense than water, hence why it sinks. Iron, more dense than glass. Aluminium compared to iron. Aluminium has a low density compared to iron, hence why it's used for lightweight bikes, window frames, so when we want the metal of aeroplanes, etc. And hydrogen, being the lightest gas, a very, very low density. The density also changes with the state of a material. So we've got the solid here, particles all tight. The liquids, the particles are free to move. And then the gases are all spread out, so they have low density. In order to find, and this is a required practical that you will have done in year 9 or year 10, how do you find the density of an irregular object with a regular object, you see? So here's a regular object, just drawing one. Very classy 3D drawing. With this, to get the volume, I can just times those two, the two sides, and then the depth. So I can get the volume of a cube or a rectangular shape, etc., a regular shape. But what this is talking about, when it says irregular, it means an odd shape. So for example here, in this example, they've shown a piece of stone. So they've got this irregular stone, it hasn't got even sides, so you can't get the volume that way. What you can do is, here we have a known amount of water. We put the stone in the water, it's gone up from, on this example, it's gone up from 28 to 30. So we can see it's gone up by 5 centimeters cubed. That means we can work out the volume. There is another one. It's a can, and you probably saw this when you did it, and it's shaped like this. It's got a water spout, and then the water is filled up to this. Oh, sorry, wrong way round. Scribble that out. It's got a can, and it's got a water spout, and the water is filled up to this level. Then you put your object into the water, here it is, and the water spills out into a measuring cylinder. So what that means is that can that can be used is called a Eureka can. The only reason I'm saying about it, you can use this method over here if you're asked about it, but if they ask you about a Eureka can, at least you know what one is. Then we've got the changes of state. And here's your normal ones. Solids can melt, turn that, solids can melt into a liquid, or they can evaporate into a gas. When a gas cools down, like water sometimes does on cold windows, it can condense into a liquid, and liquids can freeze. There is, however, two others. a few substances, like for example iodine. Iodine is a solid, and when it is heated it doesn't change into a liquid, it goes straight into a gas, and that's called subliming or sublimation. And exactly the same, iodine gas would cool down like that. So the two examples of that, in case you needed one, iodine sublimes and deposits, and carbon dioxide. When we cool carbon dioxide down, you get solid lumps of it rather than a liquid. Internal energy of particles. Well, if you imagine inside a glass of water, what this diagram shows here, inside a glass of water the particles are all moving around. Some of them have just bumped into each other, they've lost a bit of speed, some are moving freely. The internal energy of this glass of water is the total energy of all of that movement and the potential energy. So it says here the particles in a liquid or a gas are constant motion, they collide with each other and the walls of the container. In solid the particles are vibrating, but this diagram over here, all of these moving particles, all of their energy added together is the internal energy. And if you heat something up, the particles are moving faster, so therefore they'd have more internal energy. So when heat is added to a system, internal energy increases. So solid, what are the key bits? For solid, all you have to do is the particles vibrate. When you heat it, the particles gain energy, so they vibrate faster and faster until they can break their bonds. They can break free from it, and therefore they are then free to move in a liquid. But they're not free to escape from the liquid. However, when you heat them even more, they've got enough energy now to break away from the other liquid particles. So in a gas, they break free from the other liquid particles and they can move freely. When we want to know how much energy a material can store, or how much energy, we call that the specific heat capacity. The specific heat capacity is the amount of energy, I'm going to write that, it's the amount of energy it takes to take 1 kilogram of that material and heat it by 1 degree Celsius. Now water takes a lot of energy to heat up, so water is actually a good store of energy. Hot water can store lots of energy and then release that slowly. So water in radiators carrying the heat around your house, the water can be heated, and as it goes around the radiators, that energy is released through the radiators into the room. And water's a good material for that because it has a high specific heat capacity. So the equation for that, which you will be given on your equation sheet, is here. So remember this symbol here, delta, means change, so that's a change in temperature. This is the change in energy. This C stands for the specific heat capacity and the mass, and you've got to be able to rearrange that. So in this example, what it's telling us is, I need the highlighter on yellow, not purple. The kettle contains 1,400 grams of water. The water is already at 12 degrees. And it's given 400 kilojoules of heat. So first thing I need to do is I'm going to go, the mass, need my pen, the mass here is in grams and it needs to be in kilograms, so I can convert that to 1.4 kilograms, and that will go into the equation down here. The 400 kilojoules, well, the energy needs to be in joules. So that is 400,000. So that goes in here. They've told me the specific heat capacity of water is there. So therefore, I put my numbers into a calculator. I put in my 400,000 divided by 1.4 times 4.2, and I get my temperature change. Latent heat is different to specific heat capacity. The specific latent heat is the amount of energy needed to change the state of the material. So again, it's 1 kilogram, but the latent heat for ice is how much energy does it take to change it from a solid at 0 degrees, so the temperature hasn't changed. So if you're on a graph and there is your time you're putting your energy in along the bottom and temperatures up the side, what happens is the ice gets warmer and warmer and warmer, then at 0 degrees the ice will absorb the energy for a while and then it'll start to warm up towards boiling point. This here, that amount of energy, where I'm just highlighting now, this flat bit of the graph, when it's absorbing this energy, that's how much energy it took to change a kilogram of ice to a kilogram of water. Exactly the same would happen when the water boils. So there's two different terms. There's the latent heat of fusion, still messing around with my pens, here. That's how much energy you need to melt it. To evaporate the water, that's called the latent heat of vaporizing. So again, energy to change state in joules is equal to the mass times the specific latent heat. The reason why it's specific is it's different for different materials. So the specific heat needed to melt a kilogram of water is different than that needed to melt a kilogram of iron. The iron would need a lot more energy to melt. As I just drew a couple of slides ago, during this, heat is added over time, the temperature goes up. This section here, no highlighter, get this right eventually, that section there is when it's absorbing the heat to change state. That is the latent heat of fusion. This one up here, the latent heat of vaporization. When we talk about pressure, pressure of a gas depends upon the particles of the gas hitting the outside walls. So faster particles give more pressure on the outside walls, and that's why sometimes gas containers explode when they get hot. So the particles inside the gas, so in this diagram it's got that if these particles are moving faster and faster and faster and faster, they exert more pressure on the outside. So sometimes if you heat up a gas canister or a deodorant can, it will explode because you've increased the pressure. Same with balloons here. If you heat up the air inside a balloon, it can explode. Here they've got a sealed can of air. The sealed can of air is heated. The particles, the molecules of air, move faster and faster. There's more collisions with the walls on the inside, so there is a higher pressure. I'd record it as 4 bullet points. You give them more energy, the particles that is. The particles move faster, very similar to chemistry with rates of reaction. You give the particles more energy, they move faster, there's more collisions, but this time they're not reacting. This time there's collisions with the wall of the container. And then there's greater pressure on the outside. That's why sometimes in summer you have to be careful with tyre pressures, because black tyres getting hot in direct sunlight, the pressure inside the tyres is getting higher and it could blow the tyre off the wheel.